Welcome back to episode 2 or video 2, whatever you want to call it. So last time we started with a very basic relay and we built a NAND gate. And then from a NAND gate, we built all these gates. So we got a NOT gate, AND gate, OR gate, XOR gate. But even though logic gates are very fundamental, they're kind of boring. We can't really do anything with them. So this time we are going to cover arithmetic. So we're going to actually build adders. So now we can start calculating basic numbers. So we're going to start to make our simple computer kind of useful because I'll be honest, logic gates, while they're fundamental, they aren't really useful because you can do them in your head. Like you know what AND is in your head. So we're going to start building more complicated things. You can see the trend. We're going to move on. So with the half adder, we're going to start getting into binary addition. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is also 1 because addition is commutative. But then 1 plus 1 is 1, 0. And 1, 0, of course, in base 10 or decimal is 2. So we're just going to build a half adder that can add 2 bits together. So very simple. Just notice that the L column represents an XOR gate, and then the H column represents an AND gate. And there you go. That's all a half adder is. You just pass in the components, the inputs to the components separately, and then the AND gate feeds into the H. So that will already cover some of them, and then we can just get the XOR gate to cover the rest. And just to test it, it works. So there we go. Next level. So a full adder. Now we've added 2 bits together, but what happens if we want to add 3 bits? So for example, A, B, and C. So this is kind of getting, again, more complicated. We need to think about how we incorporate C into it. So pause the video if you want to try it, but otherwise, here's the solution. So we're going to use half adders. The first half adder will deal with A and B. So that will get these guys added correctly. But then we need to include C. So we're going to bring in another half adder. This time it's going to combine the lower bit of the sum of A and B and C. And then now we have, again, 2 half adders. And then the result of the lower bit should just be this output here. But the issue is, what do we do with carry? Because you can see, once we add past a certain value, we need to carry some numbers. So with that, we'll get a third half adder, and this guy will specifically deal with the carry bits. So we're just going to get carry bits. But then, since we add the carry bits never exceeded or overflowed anything. So therefore, we need the low bit to be the output. And there we go. That's all the solution. Notice how we kind of ignored the high carry bit, because this doesn't really matter. We only care about the lower bits for this adder here. Check solution. There we go. That's all the possible solution. As always, it's possible to solve with lower total NAND gates. You guys can figure that out in the comments, discuss it, whatever. But let's move on to multi-bit adder, because keep in mind, full adder only adds 3 bits. We want to be able to add any number of bits. All right, now we're going to move on to kind of like the first very useful component, which is the multi-bit adder. This can be extended to add like however many bits you want. So basically, you've created a calculator that does addition after this. So we're going to do it with 2 bits because otherwise it's going to fill up the screen and it's just going to get messy. So 2 bits will show you how it works, and then you can just extend it to any number of bits. So what we do is we are fed in 2 components, A, B, or actually technically 3 components, A, B, and C. A is split into 2 bits, so A1 and A0. B, same thing. C is just 1 bit. So in this example, we're adding binary 1, 0 plus 1, 0 plus 1. And that corresponds to the decimal 2 plus 2 plus 1, and it should be 5. And in 5, binary is 1, 0, 1. So that's how you represent 5 in binary. So we have this full adder here. And what we can do is, first of all, we're going to deal with all the low bits of these adders. So C is a low bit because there's only 1 bit. B0 is the low bit for B. And A0 is the low bit for A. So now we have all the low bits kind of handled. Now we of course need to do high bits. So another full adder. This time the high bit for A will go to A. So A1 will go to A. B1 will go to B. Okay, but now what do we do with C? Well, keep in mind, C is already adding here. So what we do is we feed the carry bit into this high bit adder, full adder. And then what we're going to do is the low bit is already set. So S0 is directly fed from here. And then S1 will be the carry version. And then C will be the carry of the carry, which is the high bit. So check solution. There you go. And this is, by the way, again, we are building a 16-bit processor. That's what NAND game wants. So it's gonna extend it to add 16. So again, it's gonna cause a lot of components if we don't do this. So now you can see it kind of wraps up 16 of those adders, or I guess 32, since it's kind of like 2 for 1. Now it adds 16. What we're going to do with increment, well, we're just going to add 1 to a 16-bit number. So now we can start entering values. So for example, we can add, let's say, 3648. We're going to add 1 to it. So how do we do that? Well, first we're going to need 3648 to be in the input. And there is a 0. So this 0 represents ground. So there's no voltage, it's just ground. What do? Well, we invert that 0, so that it always has voltage. Now it becomes 1. And then we connect this to C, and then you can clearly see we're adding 1 to it. So now we get 3649. Check solution. And by the way, this is actually the simplest possible solution. So if you guys want to figure out a better way with NAND gates, you're not going to get better than this. And by the way, look how much it abstracted away. 385 NAND gates. Imagine how much lag that would cause rendering all of those. So yeah, this is why we want abstracted components. But just know, in real life, these are all there. They're all transistors, and they're all kind of just inside your CPU. So it's kind of amazing how small those transistors are and how much you can do with them. So again, that's increment. Next level. So now we're going to talk about subtraction. So subtraction is kind of weird because computers don't have concepts of negative numbers, or just, yeah, any number less than 0. Because how can you have no negative electrical signal? That just doesn't make sense. You either have some electrical signal or no electrical signal, but you can't have negative. So we need to be clever. We need to represent negative numbers in the space we have available. And of course, the best way to do that, well, that best is arguable, but the most common way is 2's complement. And this is how your computers represent it. This is how all the architectures pretty much in the modern era does it. And to do that, we basically just noticed that we split the unsigned representation. So there's 65536 representations, including 0, in a 16-bit number. We cut it in half. We say half of it goes to negative numbers, and then half of it goes to positive numbers. So we set the highest unsigned decimal to -1. And then we start counting it downwards all the way until we get, and it wraps back around. So this is where the terms underflow and overflow come from. It's because when you get to a certain high number or a certain low number, it just starts to break and you go to negative numbers because of how 2's complements work. So with that in mind, let's try to test a few things. So we're going to test the overflow representation. So we're going to subtract 0 and 1. So I'm just going to set this inside our input as we start. Now we're going to actually build it. So we're going to add negative numbers. Keep in mind, remember, computers don't know what negative numbers are. So we're just going to have to trick it into adding negative numbers. So we're going to invert 16 of them. So keep in mind, -1, right? -1 is all F's. And then we are going to set that into B. So it's going to invert B. And then we're going to subtract B from A. So A will just remain normal. And then the C here, the C is a, so in 2's complement, you're adding the complement. So you're inverting and then you're adding 1 to it. That's how you get the representation. So in this case, we're going to get ground. We're going to invert ground. So that's just adding 1 component. And then we're going to pass it into this adder. And then finally, we will set S to 16. And then, now you can see hex is FFFFF, which is unsigned 65535. But we know with 2's complement, it's actually -1. And there you go, it matches. 0 minus 1 is -1. So there you go. That's the answer. And this, of course, is the simplest possible solution. So congratulations, we've built simple components for the fundamental operations. Obviously, we get into stuff like floating point numbers, but we're going to keep it simple for now, just so you guys can understand. All right, now we can add and subtract. But computers, one of the best cornerstone features of computing is conditionals. So how do we handle that? Well, we need to check for equality. And in this level, we are going to see if something is equal to 0 or not. This is how you implement if statements and all of that. So very useful. Even though it's not purely arithmetic, it's still useful to know. So with this, we just got to make sure all of these are set to 0. As soon as one of these guys gets set to 1, doesn't matter which one, it just breaks. So what we're going to do is we're going to use two OR gates. This OR gate will handle B3 and B2. This OR gate will handle B1 and B0. And then we're going to OR the OR gate, because if you know how OR works, it knows when it's 0. If it's not 0, it's not going to be 0. So like it's pretty sensitive to when it is being 0. With the AND gate, it's not really that sensitive because it's all zeros unless you have all ones. So again, OR gate kind of just knows. So with this triangle configuration of OR gates, it can detect if it's 0 or not. Because remember, as soon as any one of these becomes 1, it breaks the OR structure. So this is clearly wrong because we have 2 bits set to 1. It's not 0. By the way, we invert this to get the actual desired output. But look, if we set all of this to be 0, all the OR gates are 0, which get inverted to be 1. And that's the solution. The last thing I'm going to do in this video is look at if something is less than 0. So why will we need to do that? Well, with conditionals, not only do you want to check for equality, you also want to check if something is greater than or less than. So that's how we do that in computing, which is we just subtract them, and then if we see it's greater than or less than 0. So that's, again, how this works. So it gives us just one component, which is pretty strange because all our logic gates are gone. But notice that it takes a 16-bit number. So let's enter some random number here. Actually, let's make it negative just so we can see. So negative 3464. All right, now we're going to pass this into the splitter. So basically, it just takes all the 16 bits and it just kind of like independently feeds it into these channels. Notice something. If the 15th bit or the highest bit, aka MSB, so most significant bit, is 1, then it's negative. Otherwise, it's 0. Otherwise it's positive. So look, if I take the negative out, look what happens to the 15th bit. Boom. Same thing, except for now 15th is 0. Add the negative in. I pressed equal. Add the negative in. Boom. See? Toggle. Right? 15th bit is the one that's controlling the negative sign. So that's it. That's all you need to do if you want to see something is negative. You just look at the 15th bit. In this case, because it's 16-bit numbers, in any n amount of bits, you look at the n-1 bit. And there you go. That is the simplest possible solution. And there's not even any logic to this because the splitter just kind of like you take the wires and you split them. So yeah, this covers all the arithmetic section. So now we have all the fundamental components to actually do math now. So we've kind of created a simple calculator, but not quite, because how do we actually input instructions, right? How do we actually let the processor decide if we want to add or subtract? Stay tuned. That is coming in the next section. So see you then.